Mario, do you want to introduce her?
Yes. So, Laura Foglia is a brilliant student we had in Genova. Unfortunately, I sent her to Berlin with an Erasmus bursary, and she decided to stay over there with a colleague of mine, Matthias Wolf, a very bright surface scientist. And there she got involved into femtosecond phenomena. Now, for the students that I see over there, which is the typical reaction time of electrons, femtosecond timescale. So you're really looking at something in which you are delivering energy to the electron gas and not to the lattice of your system. And that's important. You can understand how phenomena evolve on a time scale which is extremely limited. So Laura had her PhD in Germany, and then she went over to Trieste and is now a beamline scientist of the free electron laser. The free electron laser is a very nice facility because it allows to make studies at the femtosecond time scale, and we had just a discussion about what could be done at an even shorter time scale. That would be to go in the attoseconds. In the attoseconds, you have the possibility to study diffraction phenomena which may occur before the electron gas has the time to react. That's really extremely challenging, and there are lots of areas in physics which could be opened up in this way. So, Laura, I leave you the floor.
Thank you. And so it's a huge pleasure to be here. I was recently thinking what would be the feeling of standing down here instead of sitting up there. And I think it's like 15 years I'm not setting foot in this room. It's a pleasure to be called a world-leading expert. Thank you very much. And I hope by the end of these 50 minutes we have to share that I will hopefully convince you that what we do is interesting and give you a different perspective on what is condensed matter physics. So the title is extremely technical and extremely complicated. It has all the ingredients of my talk. So it's an FEL-based experimental technique. FEL is a free electron laser, and I'm going to introduce during my talk what is time-resolved spectroscopy, what are the possible light sources one can use to do time-resolved spectroscopy and access these extremely short timescales. Then, obviously, I will devote most of the talk to give examples of what is a transient grating and what means to study thermoelasticity and what means then to use the transient grating to go beyond the thermoelasticity and start looking at couplings between the different degree of freedoms in condensed matter. And finally, if I have time, I will give you a few new perspectives on how this technique could then potentially evolve. So if we look at the diagram of interesting research challenges in condensed matter, what you see is that any of these different systems actually has something in common, which is that their functionality is not only dictated by the statical properties of the material, so how the material absorbs, at which energies, which is the crystalline structure, and so on and so forth, but the functionality, so the ultimate thing that distinguishes an optoelectronic device from a light harvesting device is how the different degrees of freedom couple, and if the energy actually goes from here to here and emits light, or if it goes from here to here and absorbs light. Same things could happen in quantum materials, where you have a very strong interaction between all the possible degrees of freedom. And if we look at the plot of length scales versus time scales, we soon realize that all these fundamental interactions that are at the basis of these processes all occur in the electron volt to milli-electron volt energy scale, which corresponds to time scales on the order of femto, so 10 to the minus 15, to picoseconds, 10 to the minus 12 seconds. And also, not only that, but they happen at length scales on the order of the interatomic distances, so angstroms, up to 10 nanometers or hundreds of nanometers. So we need to find techniques that are capable to access directly these time and length scales. And well, if we do a very long step back and go back to the 1878, their problem of time scales was not to look at electronic processes, but it was to understand if a horse galloping had a time where all the legs were flying or not. And this was, in the end, the very first time-resolved experiment ever. So the idea of my bridge was to set 12 cameras on a horse track and having wires on the horse track that were triggered by the horse itself. He was shooting a different image or photograph of the horse at 12 different points that were equidistant in space with a very limited exposure time, and then he was basically setting the ingredients of time-resolved spectroscopy. You need to set the horse in motion, you need to have a well-defined exposure time, and you need to have a very well-defined shutter release time between the events. And each of these times has to be shorter than the process you want to observe. So from this idea, it's very interesting that everybody in time-resolved spectroscopy uses this slide to explain what we do, because actually the Nobel Prize in 1999, so Zivile, used these very same pictures to explain his Nobel Prize in the Nobel Prize lecture. So yeah, from the horse galloping to femtochemistry. The idea in femtochemistry is that you set the horse in motion with a laser pulse that is extremely short, shorter than the process you want to look at. And then you have a very well-defined exposure time, which is the duration of your probe pulse. And you have a very well-defined delay between the excitation path and the probe pulse, which is set by moving the delay line, so-called delay line, so making the probe go on a detour with respect to the direct beam, which is controllable because mechanics is controllable on the nanometer or micrometer length scale, which corresponds to femtoseconds, and then you have a very well-defined delay between your excitation and your probing time. And you can then repeat this experiment over and over again for different pairs of pump and probe pulses that arrive at different delays and reconstruct a similar film to what we saw before with the horse. Obviously, to do this over and over again, you need a fourth ingredient, which was not the case in the case of the horse, and it is that the material must recover between the pairs of pulses that induce and probe the phenomena you're looking at. So for non-reproducible phenomena, this is actually not the technique, and you need to do different approaches that we don't have the time to discuss today. There is another condition. So if every time I trigger my system, the phenomena I want to look at reacts in a different way, I'm not going to be able to do statistics. So what I need to do is to have a coherent excitation of my phenomena. So every time I trigger my system, I need to have my man moving in the same way. And to do that, I need a trigger that has to be short and has to be intense. So to give a more concrete example, let's think about driving a phonon. So if my trigger, my excitation pulse is longer than the phonon period or in the same order of magnitude than the phonon period, photons that are at the head of the pulse will drive one oscillation, but also photons that are at the tail of the pulse will drive an oscillation. And then what I will see in the end is basically nothing, an average of these incoherent oscillations. But if my trigger becomes shorter and shorter, at some point, all the phonons in my system will wiggle at the same time, and I will have a very well-defined signal in my experiment. So the relevant parameters for a trigger pulse, what we call a pump pulse, are obviously the wavelength. And the wavelength is important because it's resonant to different processes in condensed matter. The so-called time-integrated power density, which is typically expressed in millijoule per volume, or the fluence, which is millijoule per surface unit, the pulse energy in millijoules, and the pulse duration because of this reason, and also sometimes the peak power. Another important aspect is also that your camera shutter has to be also short because it defines your time resolution, but it has to be weak because it has to be non-perturbative. So you don't want your probe, your camera, to interact with the system you're looking at. So now that we have all the possible ingredients, I want to show you something different. I mean, obviously, lifetimes of condensed matter phenomena were investigated and were studied even before we had ultra-short lasers and femtosecond lasers. And what you were doing was to do inelastic scattering, and you were looking at the line width of your inelastically excited phonon or magnon or whatever you were looking at. So there is a direct, obviously, relation between time-resolved and energy-resolved experiments. So the time resolution, which is defined by the length of our pulse, corresponds to the maximum energy you can access with a frequency-resolved experiment. And the time delay range, so how long you actually measure this oscillation, since you then have to Fourier transform it, will define your minimal energy resolution. So basically, these are the typical numbers. We work in the order of 30 to 300 femtoseconds, and we have a time range which goes from 10 to 1 nanosecond, so 10 femtoseconds to 1 nanosecond, which typically correspond to roughly maximum 200 terahertz accessible energies and an energy resolution on the order of 4 micro electron volts. It is easy to improve the resolution because you just have to measure for longer time delays. I mean, easy if you have a lab and you can stay there for weeks measuring. But it's much, much harder to measure the highest, to improve the highest accessible energy, because this is basically limited by the single cycle regime of your pulse, which is about 3 femtoseconds if you work at 1 micron wavelengths, and becomes on the order of the attoseconds if you work in the soft X-ray and hard X-rays. So what is the idea behind this? Why do we want to do this? Well, fundamental processes in condensed matter have different timescales. So we start with the absorption processes, which are on the order of the atto to femtosecond timescales. But then you already see that the carrier-carrier scattering is already on the femtosecond, and femto to picosecond is the time electrons take to interact with the lattice. And then you have basically the processes that lead to ablation and evaporation of matter, or that lead to thermal diffusion, thermal expansion, and so on and so forth. So you can differentiate processes by their timescales. If you do a measurement and you see something that evolves and then decays on the femtosecond timescale, and then you have something that grows on the picosecond timescale, most probably the first thing you see is an electronic interaction. The second thing you will see is a lattice phenomena or magnetic phenomena. And also you can separate processes by their wavelengths. So going from the infrared and the visible towards the X-ray wavelength will allow you to do imaging and directly visualize atoms and nuclei, but also each of these wavelengths is resonant with different fundamental interactions in matter. So you have vibrations that absorb in the terahertz and infrared wavelength. You have the valence electrons the ones that are responsible for the functionality of the material that typically absorb in the visible or in the near ultraviolet. And then when you go to the soft X-ray and X-ray, you start interacting with the deeper electrons close to the nuclei. And those electrons are the ones that have some information on the chemical specificity, so on which element is present in my crystal. So this will give me the signature of the chemistry of the material I'm looking at. So in this introduction, I hope that I've kind of shown you that the interplay of spin, lattice, and charge subsystems defines the functionality of relevant materials for condensed matter. And it also defines what are their transport phenomena, what are their so-called collective excitations, phonons, magnons, vibrations, and so on and so forth, but also leads to exotic non-equilibrium states or even phase transition phenomena, and that we can selectively investigate by choosing the right time scale and the right phonon energy, the time evolution of these different degrees of freedom. And the idea is that to take the femtochemistry, which was evolving in the late 90s in the visible range, and extend it to the XUV and X-ray regime in order to gain information on the chemical specificity of the system, and also, as I was saying before, accessing larger exchange momentum and smaller length scale. And the exchange momentum is important because typically, for instance, in quantum system, the couplings between the different degrees of freedom occur at the gigahertz range of frequency and at the edges of the Brillouin zone. They don't happen in the center of the Brillouin zone. So if you are interested in looking at couplings, you need to go to a higher momentum. So how do we do that? I was saying femtochemistry was developed in a laser lab. And when we were back in the 60s, we were sitting in this diagram of light sources versus photon energy and pulse duration, basically here. Tabletop lasers and cyclotrons had roughly the same photon energy and pulse duration, and then the two communities developed in an orthogonal axis. So the synchrotron community went higher and higher in photon energy to gain more and more chemical selectivity and higher resolution for doing imaging or diffraction. Whereas the tabletop community, the laser community, went shorter and shorter in the pulse duration to go strongly out of equilibrium, so try to understand in the lab how stars work, how nuclear fusion works, and so on and so forth. Or it was exploiting the temporal coherence, so the short laser pulses, to do nonlinear optics, coherent control, mixing of frequencies, and learn deeply how the interaction between light and matter works. And we had to wait until the 2000s, so the first X-ray free electron laser saw the first light emission in 2010, to try to start thinking about combining these two worlds and joining these two communities, and to try to think to do time-resolved spectroscopy in the X-ray range. So to explain what an X-ray FEL is, I need to do a very short excursus on synchrotron radiation. Somebody sitting here in the audience knows I hate formulas, I hate theory. It's really hard for me to speak in terms of mathematics, so I will try to be as simplified and easy as possible. Synchrotron radiation is present in nature. It was observed, for example, in the Crab Nebula, and it's the light that high energy electrons or relativistic electrons emit when they spin around the pulsar at the core of the nebula. So when an electron is in a magnetic field and it's accelerated in a curved trajectory, if the electron is relativistic, it emits electromagnetic radiation in the X-ray range. It's nothing else than a relativistic antenna. So if we think about an antenna, a classical dipole antenna. We have our electron oscillating up and down, and this electron will emit in the classical dipole pattern. But if our electron is moving almost at the speed of light, then the emission will no longer be the classical dipole pattern, but we will have a length contraction and a Doppler effect that will lead the emission to be tangential to the trajectory and have a very narrow cone. And this is basically what is exploited in synchrotrons, especially in the so-called bending magnets, where one has a circular accelerator where the electrons run around in circles almost at the speed of light. And then every time they are on a tangential trajectory, they will emit radiation, which frequency depends on their relativistic energy along the tangent of the curve. Then you can take the same concept and make the electron go up and down and wiggle around. This is the so-called wiggle radiation. Or you can even make this orbit much smaller, which is the undulator radiation. And when the orbit becomes smaller, the electron that is sitting here and the electron that is sitting here and the electron that is sitting here will emit all at the same energy. And you will have interference effects between the emission of all the different electrons along the trajectory. And then your radiation is no longer a broadband spectrum, but it has very well-defined peaks at a wavelength that is, we will see it in the next slide, is basically associated to this deflection parameter K. So bending magnets, wigglers, and undulators are at the core of what is called a synchrotron facility. In a synchrotron facility, you have electrons that are accelerated in this ring, which is typically nowadays the booster, and then they are injected in what is called the storage ring, where they start running around and losing energy in form of X-ray photons that is then collected along the beam lines where the experiments are carried. So I need to go from the undulator radiation in order to explain what an FEL is. So how does undulator radiation work? Well, we have a relativistic electron which sees an electromagnetic pattern and is forced to run in this undulatory trajectory. It has its own energy and then a Lorentz factor. But this electron in its own frame sees this wiggling trajectory as contracted because of relativity. And when it starts oscillating in this kind of its own dipole frequency, and we transform it back to the lab frame, the dipole frequency will have another contraction, another gamma contraction, and in the end, the electron oscillatory frequency, which would be lambda u, the period of the undulator, is contracted twice. So you can go from something which is in the order of centimeters for a typical undulator down to nanometer radiation just because of this double division by the Lorentz factor. So as I was saying before, at specific wavelengths, you have constructed interference. So the undulator radiation is characterized by sharp peaks at the fundamental harmonics. It has these numbers, but the most important thing is that the undulator radiation is incoherent. So if you start having more than one electron, each electron will wiggle at its own frequency given by its own energy, and in the end, you will just have yes, they will all have the same frequency, but they will have different phases, and their intensity will just scale with the pure number of electrons. But I promised you a laser, so how do we go from this to something that's fully coherent and is short in time? Well, a typical laser has three main ingredients. And you need a so-called gain medium. So in the visible, a laser has a crystal. In this case, our gain medium is still the electron bunch. I don't see the pointer anymore here. Then you need a resonator, which typically is a cavity in a laser. And here is nothing else than a very long undulator chain. And then you need something that launches the emission. So a laser is light amplified by spontaneous emission radiation. Here, our spontaneous emission is the synchrotron radiation occurring at the very beginning of the undulator chain. And then what happens to our electrons? So they start as a packet which has a given density, and the packet is typically much larger in space than the wavelength of the emitted light. And then if the undulator chain is long enough, these electrons are not only emitting light, but they are interacting with the light that was emitted by the neighbors just behind them, and by the light that they emit. And then basically, the electrons that are sitting close to the maxima and the minima of the electric field of the light that they are emitting will gain momentum if they are in phase with the field, or will lose momentum if they are out of phase with the field. And then, since they are in a magnetic field, the orbit will also change. And you see, you have a sort of self-organization of your electrons. And along the so-called gain length, you will start having electrons that self-organize into packets that have exactly the same spatial distribution as the wavelength of the light you want to emit. And then all these electrons sitting here will emit light in phase, no longer out of phase. And you will have an exponential gain of the emitted intensity along the undulator chain. And you see typical FEL lengths, undulator lengths are on the order of 100 meters. And the light is now self-amplified spontaneous emission. So it's coherent, and the intensity grows as the square of the number of electrons. Okay. This is the working principle of so-called self-amplified spontaneous emission free electron lasers. They are a very special class of accelerators, and there are 7 running free electron lasers. I only have 6 here, and it will clear in a second why. It will be clear in a second why. So these are the parameters of the only 6 accelerators that work in this working principle. And the final emission of a self-amplified spontaneous emission laser is nothing else than this spike of wavelengths. Each of them is coherent by itself, so we don't have temporal coherence between this wavelength and this wavelength, but we do have temporal coherence or phase between the different spikes of the SASE pulse. And this is in principle easy to realize. You just need an accelerator, obviously, but you have it at synchrotrons typically, and you need a very long undulator chain. So self-amplified spontaneous emission FELs are on the order of kilometer-long machines. And well, in Trieste, we didn't have a space for a kilometer-long machine. So we tried to do what is the next step of laser amplificators, which is the seeding process. In the seeding process, this, what is called micro-bunching, so this patterning, self-patterning of the electrons, is no longer growing from noise, but is induced by a real laser, real in terms of visible, with a given wavelength. So this laser interferes with the electron bunch in a special magnet, which is called the modulator. And then we have a controlled patterning of the electrons, and this controlled patterning is amplified in the undulator chain. This gives a very different spectrum because the final emission is fully controlled by the wavelength of the laser, and the light that we get is fully coherent also in time. So all these photons are in phase with each other, it has a very high shot-to-shot stability because it encodes the properties of the original seeding laser. Also in terms of wavelength, obviously, because we are doing harmonics of it, but also in terms of pulse duration. This works only up to roughly 16 nanometers. If we want to go even lower, so 70 electron volts, if we want to go even lower in wavelength or higher in energy, we need to repeat the process twice. This is the fresh bunch. And it's important for me in the end because the fresh bunch technique gives you two colors. So you have a first amplification process, and then the light that was generated in this first amplification process interacts again with the electrons on a non-spoiled part of the electron bunch and generates a second pulse. So we now have two pulses. The final wavelength emission, or the higher wavelength, is just given by the product of the two harmonic numbers. And this can go up to harmonic 60, which is, if you start with a 266 nanometer laser, it's the carbon edge. So we go up to 300 electron volts. And now we have access to almost all the important and interesting core levels. Two colors is so important to us that we started also developing fancy accelerator schemes where we divide the undulator chain into two parts and do two colors, and these two colors will be overlapped in time. And if I have time at the end of my talk, I will show you an example where even the polarization of these two pulses was different. So now I have all the ingredients for what I'm going to show you afterwards. I have a facility, which is this linear accelerator, which, as any other free electron laser in the world, is sitting next to a synchrotron ring. Typically, you need the knowledge of the people that were working for years at the electron ring in order to develop such facilities. It has roughly 200-meter long injector and linac. Then we have only 100 meters of ondulators, because we don't need such a huge gain as in the case of the self-amplified spontaneous emission facilities. And then we, the beamline scientists, are confined down here in this 50 meters long experimental hall. In the experimental hall, we have 5 different XUV beamlines. So these are the ones here. And one that uses the residual terahertz emission that is emitted when the electrons at the end of the linac are, what did I do? Okay. At the end of the linac are basically launched into their beam dump, and then they emit terahertz. Okay, now let's take a break and a breath and move on. I was saying at the beginning of my talk that we are interested in measuring couplings between fundamental excitations in matter. So this is a plot of typical collective excitation and their wavelength or energy dispersion as a function of exchange momentum, so as a function of point in the Brillouin zone that we are looking at. We have here the magnons, the phonons, well, the phonon lifetime, which also scales with the momentum, and thermal diffusion as typical examples. And you see low exchange momenta, so very close to the zone center, can be accessed by optical spectroscopy, so in particular Raman spectroscopy, transient grating spectroscopy, or Brillouin scattering. Very high exchange momentum can be accessed typically with inelastic X-ray scattering. This was a frequency resolve technique that I was trying to explain before, or even with neutrons. But there is a gap. And this gap is in the range of the 0.1 to 1 inverse nanometers, which corresponds roughly to the 100 to 1 nanometer length scale. And this is a particularly interesting length scale if you are thinking about disordered systems, so if you want to study vibration in glasses, or if you are thinking about processors and nanotechnology, because actually we are now thinking about doing processors in the 10 nanometer or 7 nanometer range. And this gap was not accessible by any experimental technique available, which was not implying to produce a pattern on top of your device. So like do etching or modifying your material. And well, we started thinking what to do, how to access this, and the idea was to take this transient grating technique and extend it to the ultraviolet or extreme ultraviolet wavelength range. So to explain what is transient grating, people typically think in terms of nonlinear optical interactions. And this is because transient grating requires 3 laser pulses interacting with each other. So the idea is that if you have electric fields incident on a material which have very strong strength or field strength comparable to the interatomic fields, your material is no longer behaving linearly. So it's not just absorbing or reflecting light, but you have higher orders in the susceptibility tensor, and this basically couples the field of one of the beams with the field of the other with the field of the other. This is the so-called wave mixing phenomena, and it's used in a laser lab, or it's even used in this laser pointer. Not this one, no, because it's red, but typically in green laser pointers to transform the green light so the red light into green, to up-convert the photon energy. You just mix 2 electric fields and you create what is called the sum frequency of the two incident frequencies. So second order interactions only work in media that have no inversion symmetry. So it's used typically to study surfaces. Third order interactions are the first non-zero order in all materials, and this is what is called four-wave mixing. And transient grating is a four-wave mixing technique. So as I was saying before, it's actually the easiest four-wave mixing technique because you have 2 electric fields which have the same frequency, same arrival time. And as you know, if you take 2 beams, I hope you know, if you take 2 beams of the same energy, of the same frequency, and you cross them at the same time in the same spot at a given angle, you create a stationary wave. And this stationary wave is what we use to drive the excitation in our material. So our sample, our crystal, will see minima and maxima of light. And this minima and maxima of light will drive an excitation, but also will act as an effective diffraction grating for a third beam, which arrives at the delay time, and which is then diffracted at the Bragg angle. This patterned excitation, which excites electron here, but not here, here, but not here, is then associated also to an exchange momentum, a selected wave vector, which is given by the frequency of your excitation beam and the crossing angle. I don't like to think about transient grating in terms of nonlinear optical interactions because it's actually not needed, in the sense that, as I was saying, we are doing nothing else than a patterned illumination. And a pattern illumination by itself, it's not a coherent wavelength or wave mixing interaction. So it's much easier to think of what we do on the sample by looking at this diagram. So again, we have our standing wave excitation. This is exciting electrons here. So if we have absorption, we will have also electronic excitations that are patterned with the same periodicity. And then these electrons relax and they couple to molecular vibration, or even excitons which have this periodicity, and so on and so forth. These electrons heat up your crystal, and then you have an effective thermal periodicity or thermal grating in your sample, and then you can measure its diffusion, and you can do thermoelastic expansion or even magnetoelastic coupling phenomena. And then you have the 2 exotic cases, the case of the strain which is driven by the field, will be the real nonlinear optical interaction. But it's not happening in the XUV simply because XUV light is absorbed by any material on the world. So you never have something that is only field-driven in absence of absorption. And then the polarization grating, which would be the end of my talk, which is an exotic case when the two beams no longer have the same polarization but have opposite polarization because they cannot interfere. They don't generate a standing wave, but they do generate a polarization wave. And I hope I have the time to show you that as well. So yeah, these would be then the 3 topics of the talk. And again, to summarize, we have 3 beams. This has an exchange momentum. And then we built a whole instrument at the FEL that had exactly the right angles and wavelengths to cover this wavelength range. So these are just the numbers of the beamline, but the beamline works like this schematically. We have a mirror that splits the beam into 2 parts. Half of the beam will be the probe beam, goes through the delay line I was showing you in the second slide. And then I have another mirror that splits the remaining half of the beam again into 2 parts. And these 2 parts are the ones that drive the excitation. These are typical numbers we can access. And the instrument is working so well that it's now the most requested instrument of the Fermi free electron laser. And this is because, well, it has a well-defined scope. So we have 1 experiment, and we are doing only that. And obviously, it has also the drawback that we have 1 experiment, and we are doing only that. And the community is actually a bit limited. So this is the instrument. It's a 20-meter-long interferometer in vacuum, because, again, XUV light is absorbed by everything. This is the delay line, the multi-layer delay line, and these are the chambers that contain all the 4 different focusing mirrors for changing the crossing angle at the sample. And now I will just give you some examples of what we can do. Oh, no, I forgot I had this slide again. Again, this is to remind how it works. So we have this excitation pattern. This excitation pattern drives electronic excitations in stripes. These electrons interact with themselves, thermalize, interact with the lattice, and then we have this heating pattern. And this heating pattern expands the crystal in some areas, whereas it does nothing in some others, and so on and so forth. So this is the thermal patterning, or this would be the magnetization pattern in a magnetic system where your light excitation induces demagnetization, and your dark areas of the pattern don't do anything. And then you look at the intensity of the diffracted beam and measure as a function of time the time it takes from going from this situation to this situation. And the fundamental spatial limit of this technique is only the mean free path of the originally excited electrons, because you need to preserve this periodicity down to the picosecond time scales in order to have all the interactions taking place. But if your electrons are excited and just diffuse to the dark stripe fast enough, your contrast will be canceled before you can produce any other excitation. So this is basically the fundamental periodicity limit. Okay, it was used to study thermoelasticity. So my title was Beyond Thermoelasticity. I hope I arrived to Beyond Thermoelasticity. And this is basically because we have these density fluctuations, and anything absorbs in the XUV, so the variations of the refractive index are associated to the variations of the temperature. And then what we measure is an acoustic waveform as a function of delay, and this is a bulk transverse acoustic phonon on cobalt. We did this for several different samples, for several different periodicities. We can map the velocity of these frequencies as a function of exchange momentum, and this is the acoustic, the speed of sound in silicon nitride. We can map the dispersion, and this follows exactly the Q-square dependence one would expect for acoustic phonons. So the experiment works, and this is nothing else than simulated scattering of EUV light. It can be used to measure thermal transport, because when you have heating sources that are smaller than the phonon mean-free path, you cannot longer describe heat transport in terms of Fourier law of diffusion. And then you need to directly measure the decay time of the phonons, and this is an example for silicon, which you would expect to be extremely well studied, but nobody had ever measured before the heat diffusion of silicon at hundreds of nanometers or tens of nanometers length scales. We can measure surface elasticity, because not only your bulk expands, but also your surface. And this is done then in back diffraction, so in reflection. And this is strontium titanate, and you just see the beautiful oscillation of the surface elastic wave, first when it's coupled with thermal diffusion, and then after the decay of thermal diffusion when it's alone. And this was the highest ever surface acoustic wave measured on a sample without any kind of patterning. And the idea now would be, I keep moving this, would be to couple these surface acoustic waves to spin waves and study magnetoelasticity. And then if you want to go beyond thermoelasticity, you need another ingredient. You need a resonant probe, because you no longer want to be only sensitive to the change in temperature, but you want to be also sensitive to your electronic system. And then, for example, in the case of cobalt, which is a magnetic material, you start having circular dichroism interactions, and you see the electronic response. Same material, same periodicity of the transient grating, two different probe energies, two completely different responses. And this was used then to study nanoscale magnetization transient gratings, where you demagnetize your system again in patterns. And the idea here is to measure the spin transport. So we have a very big magnet to put our sample in and accommodate the large 54 degrees crossing angle. And this is what you see. This would be the elastic acoustic oscillations, and this is the magnetic response when you crank up the field of the magnet. If you do periodization of the light polarization, you see that the signal at resonance, so when you are measuring directly the electrons that are responsible for magnetism, is dominated by the magnetization response. Then I had a lot of examples. You can play the game of the so-called all-optical switching, which is something that is very interesting for applications, which is the idea of switching matter with light. So in all-optical switching, your pattern is no longer sinusoidal, because you physically induce a phase transition. And this means you have also a second order of diffraction, and then you can observe how the time evolution of this second order of diffraction goes on. This was just to show that we could measure all-optical switching with a transient grating, and then the next question was, what is the fundamental limit, spatial limit of this? And it was demonstrated that basically what you need for all-optical switching is to dump a lot of energy in your magnetic system. You have your ferromagnet, you dump a lot of energy, and you invert the spins of both sublattices of the ferromagnet. And the point is, how much energy can you dump into this system before it breaks? And this is nothing else than asking how fast does the heat dissipate before your system breaks. And indeed, the experiments, we have done experiments from 100 nanometers or even longer down to 17 nanometers, show that this is the damage threshold of the material, and all optical switching can occur only at periodicities where you dump enough energy before you cross the damage threshold. And the last possible point where you induce all optical switching is actually 25 nanometers, roughly, in cobalt gadolinium, which is one of the most efficient all optical switching materials, because basically it has a very small heat diffusion. So it keeps the excitation there where you put it. And then just to close, I want to show you that we can also induce coherent magnons. So we not only induce vibrations of the lattice, but we can also induce spin waves. This requires a special geometry of your magnetic field, which has to have a very strong component along the propagation direction of the probe beam. So we had to do it for a tilted magnet, and you see in this sample for 0 angle of the field. So when the field is parallel to the transient grating, you don't induce vibrations and or spin waves, and then for higher, the higher is your angle, the higher is your magnon. This was a different magnetization orientation of the sample, and then you already had vibrations at 0 angle, but if you switch off the magnets, then your signal disappears, so the signal was definitely of magnetic origin also in this sample. And then you can do it for different periodicities and map the dispersion. So this is the magnon dispersion. I had a lot of information for specialists in the field here, but the take-home message here is that we finally have a tool for measuring spin waves in the range that it's not covered by Brillouin nor by neutron inelastic scattering. So we can finally measure the coupling between spin waves and other fundamental excitations in matter. And I think I'm already over time, but this is just the newest perspective I want to show you. We did the same. We are, for now, the only end station in the world where we can do this kind of experiments. But since June of last year, we have demonstrated transient grating can be done also in the hard X-rays, which has complementarities because it basically allows us to access also the bulk of materials and buried interfaces. And this, if you can see it, is the transient grating signal, the little spot next to the diffuse scattering at the 222 Bragg peak of STO and the truncation rod. So in between, you have the little tiny transient grating dot. This I will just skip. And this is the summary of everything that we can do with transient gratings. I could have talked for, like, I think 2 or 3 hours easily if I had to touch all the possible experiments we can do. We can do confined phonons. We can do ultrafast electronic responses and photo-induced phase transitions. And I was discussing with Nicolas today that we can even try to measure the superconducting coherence length. And, well, I skipped the spectroscopy slides. I skipped the pulse metrology part. We can use the structured illumination to do microscopy. And this is then the highlight of the new thing that we can do, which is also play around with the polarization. And with this, I need to thank all the people that have been fundamental in developing this instrument, and obviously for your attention. I hope you are not completely knocked out. Oh, you are. was amorphous, yes.
And you also, in some way, emphasize, not too much, but you emphasize that when you make measurements with this stuff, the sample is not so glad, usually.
It's not?
It's not so glad, usually. Usually, the sample in the end...
Not on this
In the
particular-
case of the amorphous silicon nitride, what was the fate of the sample? And the question is, the amount of energy that you put into the sample led to some, for example, crystallization, some transition from amorphous to crystals and so on?
Okay, 2 steps. The experiment you did 9 years ago was a different instrument, and it was an instrument that has nanofocus and which is actually devised to dump a lot of energy on the sample and make it explode. In dialect, we say squagliamo atomi. So we basically liquefy atoms. The transient grating experiment, in the end, we wanted to be a probe, so really a spectroscopy. So it has a much bigger focus. The light is focused in the order of 200 to 300 microns on the sample. And we work with extremely low fluencies of the FEL. So we never observe any kind of deformations. We can print permanent gratings. We have done it. We have done it for studies, but we typically also do it for alignment, in the sense that we just print the grating onto the sample, we ablate it in stripes, and then we have something that we know where it diffracts and where we can put our detector in the end in order not to get crazy to look for a signal. But in a typical experiment, then we reduce the excitation down to below the damaging threshold. Indeed, there was an experiment which should see the publication soon, I hope, from the Trento group on glasses. They wanted to look at this bosonic bottleneck in the mesoscopic range of glasses. And they were measuring a glass at 40 Kelvin. And from the frequency of the waves we have observed, we can also estimate the temperature rise that we induce in the sample. It's not negligible, so it's on the order of, I think, on the highest fluence, they were increasing by 80 degrees the temperature of the lattice at the end of the process. But still, it's not enough to melt. I mean, you start from 40 Kelvin, so the heat capacity is also much lower, and then you effectively heat up much more than when you work at room temperature. So yes, this is the order of excitation energy we dump into the system.
We may have time for another quick question.
Thank you for the nice talk. Since you mentioned, is related with the previous question, since you mentioned that you are controlling very well the intensity, I was wondering which can be the impact of this approach for novel materials such as layered nanostructures, so on, so beyond bulk, like, do you see something?
Yeah, I mean, I have a proposal myself, which is evaluated since I think 4 runs not extremely well by the peer review panel, on doing moire patterns on like these boron nitride heterostructures, which have already a moire structure, and then I want to drive this moire or change this moire interaction by using the periodic excitation. The problem the panel sees and keeps seeing is that 2 monolayers will be extremely weak signal. So I think it's a matter of trying and trying and trying and see what are actually the limitations of the technique. So this beamline is online since 2017. And yeah, in the last 9 years, we have first done the commissioning, and it's roughly 2 years that we work on full regime. So if I had shown you the very first measurements, the signal to noise was terrible. And now we have pretty nice traces.
Fantastic. Let's continue discussion over refreshments outside. And let's thank our speaker.